So in this video, we will be talking about eliminating the parameter. So we were talking about parametric equations and how we can graph them, how we can parametrize them. And now what we want to do is that given a parametric equation, so if I give you some equations in parametric form, you want to turn them back into x and y. So in the previous problem, we were graphing this set of parametric equations, and when we graphed it, we said that it looks like a parabola. So basically, let's try to find this equation of the parabola using the parametric equations. Okay, so what we're going to do is something called eliminating the parameter. So basically, the way that eliminating the parameter works is basically you want to get rid of t. So the way that you kind of do it, the first thing is you want to solve for t using one of the equations, whichever equation. Usually one of them is easier to solve for t than the other. Then you want to plug into the other equation. So once you solve for t, you want to plug it into the other one. And then one of the things that you have to make sure is that you have no t's. So make sure you have no t's. Okay, so basically what you want to be able to do is do these steps, and then you'll be able to figure out the x and y. Now sometimes you can't solve for x and y. Sometimes you will, sometimes you won't, but it really just depends on the scenario. So let's do this example. So eliminate the parameter. Okay, so let's say you had the previous one, x squared minus 2t, and then y equals t plus 1. So the first thing that you want to do is solve for t. So you can kind of see that solving for t on the first one might be a little hard because you have a square here. So it might be easier to solve for t here. So I'm going to subtract by 1. So you're going to have t is equal to y minus 1. And now that I solve for that, what I'm going to do is I'm going to plug it into this equation. So then you're going to have x is equal to y minus 1 squared minus 2y minus 1. So if I FOIL this out, you're going to have y squared minus 2y plus 1. And then when I FOIL this guy, it's going to be minus 2y plus 2. So then you're going to be left over with x is equal to, so the y squared stays there. This and this is going to give me negative 4y. And then this guy and this guy is going to give me a positive 3. So you can see here that you can't quite solve for y. Instead, we solved for x, which is basically fine. And actually, this is the equation of a parabola. Notice that this looks very much like y equals x squared minus 4x plus 3. You can kind of see that these are kind of a little bit, they have a little bit of a resemblance. And actually they do, because if I were to graph this in x and y, like the one in blue, then you know that you're going to have a parabola that's going up and down, so a happy parabola. However, you have the one in purple, which I'm going to draw in green, you actually have a sideways parabola going this way. So we're going to talk about these parabolas later on and how to graph them. So far we've talked about these guys, which are functions. These guys are not functions because you can see that it doesn't pass the vertical line test. So, but yeah, this would be the equation in x and y. Notice that there's no t's here, which is going to be what we really want. So let's do a couple more examples. So we want to eliminate the parameter. Okay, so here's the other problem. So let's say we have x of t is equal to t squared plus 1, and then y of t is equal to 2 plus t. Okay, so what I like to do first is that I want to get rid of this x of t and y of t. I'd rather just write x equals t squared plus 1, and then y equals 2 plus t. I like writing it this way. I mean, I don't see a reason why you would want to write x of t. These are functions of t anyway. So, but I would do this extra step. Your book does it that way. So notice that solving for y for t on the y is a little easier. So I'm going to subtract the 2 over. So you have y minus 2 equals t. And then we're finally just going to plug it into the other one. So x is equal to y minus 2 squared plus 1. So you can leave it like this. You can FOIL it out if you want to, but this is good enough. Okay. So b, let's say we had x of t is equal to e to the negative t, and then y of t is equal to 3e to the t. Okay, so one of the things that I want to do, let's write it as x equals e to the negative t, and then y equals 3e to the t. So let's start off by solving. I think this one might be a little easier. Well, it doesn't really matter. So remember, to get rid of that e, you have to take the natural log. So I'm going to take natural log to both sides. Okay, so then you're going to be left with ln of x is equal to, this goes away, negative t. And then we're just going to divide by that negative, so t equals negative ln of x. And now we're going to plug it into the other one, so you're going to have y is equal to 3e to the negative ln of x. Okay, one thing that I can do is I can move this negative to the top using properties of logs. So you have 3e to the ln of x to the negative 1. Then you can kind of see that the e and the ln will go away. So then you have 3x to the negative 1, which is just 3 over x. Okay, and you will find out later on that y equals 3 over x is basically a hyperbola. That kind of looks like this. Okay, all right, let's do one more. So let's say we had x of t is equal to the square root of t plus 2, and then y of t is equal to the log of t. So you can solve for whichever you want. Actually, it doesn't really matter which one you solve for. I'm going to solve for x. So for this one, and then you have y is equal to log of t. I'm just going to use this one. So I'm going to subtract by 2. So you're going to have x minus 2 is equal to the square root of t. I'm going to square both sides. So then t is equal to x minus 2 whole quantity squared. And now I can plug it in there. So y is equal to log of x minus 2, and this whole thing is quantity squared. Notice that I can probably put the squared in the front. You got y is equal to 2 log of x minus 2. So this is basically the equation. All right, cool. All right, so now what we're going to do, now that we kind of practiced eliminating the parameter, I want to do one last problem where we can graph it, but now we're graphing parametric equations with trig functions. So graphing parametrics with trig. Okay. So let's say we wanted to graph this. So x is equal to cosine of t, and y is equal to sine of t. And let's say here t is between 0 to 2 pi. So we only want to put in values that are from 0 to 2 pi. So we have this set of parametric equations. So the first thing that we kind of want to do is set up a table. So we're going to set up our t, we're going to set up our x's, and then we're going to set up our y's. So for t, it'll be smart because we're looking at cosine and sine. It'll be smart to look at 0, pi over 2, pi, 3 pi over 2, and then 2 pi, which are the quadrantal angles. So now let's go ahead and plug in 0 into the t. Notice that I'm going to get a 1 for this one and then a 0. Then plug in pi over 2, so you're going to get 0 and 1. So then when I plug in pi, you're going to get negative 1 and 0. 3 pi over 2, you get a 0 and a negative 1. And then when we complete a full circle, you're going to get 0, 1 and 0. Okay, so let's go ahead and graph it. So remember that t in this case are your angles, so you have t equals 0, right? So at t equals 0, you're going to have the point 1 comma 0. Which is basically here. Let's just say this is 1 comma 0. So this happens at t equals 0. At t equals pi over 2, you have 0, 1, which is this one. So t equals pi over 2. t equals pi is going to be right here, negative 1 comma 0. That's t equals pi. 0, negative 1, that's going to be at t equals 3 pi over 2. And then we're back here at t equals 2 pi. So basically what you can kind of see is that this graph, and it should come to no surprise, it should actually be the unit circle. So this actually is a unit circle. Now we gotta make sure that we graph the orientation of this. So we have to draw little arrows pointing counterclockwise. Okay, so that would be my parametric curve. So it's no surprise that this should actually be the unit circle, okay? So, so basically we can parametrize the unit circle using cosine and sine. Now, let's say I wanted to eliminate the parameter, okay? So can I find out what the equation in just x and y without the t is? So eliminate the parameter. Okay, so can we try to eliminate this parameter? Now, there's two ways that I'm going to show you how to do it. The first way, because we're dealing with trig functions, it'll be nice to use an identity. And one of the identities that we know is that cosine squared theta plus sine squared theta equals 1. So that's one of the identities that we know. So let's just write it in terms of t, because that's what we have. So this is cosine squared t plus sine squared t equals 1. So that's what we have. Okay, and now all we got to do is look at our parametric equations. You can see that cosine of t equals x, sine of t equals y. So let's just plug that in. So this is going to be x, and then there's a square there, plus y, and then there's a square there, equals 1. Here, typically, we don't have to solve for y or x because we know that a circle does not, it doesn't pass a vertical line test, so it's not going to be able to be solved in terms of just y by itself. So this would be the equation of a circle. Okay, so that's how you kind of do it using an identity. But let's say you wanted to do it algebraically, just how we were doing it before solving for t. So algebraically, it's going to take a little bit more work. So I'm going to write algebraically. So we know that x equals cosine of t, and then y equals sine of t. So can we possibly solve this just by solving for t? Well, we actually can. So let's just solve for y first. So we know, well, let's do this one instead. So we can apply cosine inverse to the other side. So you're going to have cosine inverse of x equals t. So now we're going to plug it into the other one. You got y is equal to sine of t, which is just equal to cosine inverse of x. Okay. So this basically doesn't look like an equation of a circle, right? So we don't get x squared plus y squared equals 1. We got something weird. So is this x squared plus y squared equals 1? Well, we're not done yet. So one of the things that we can do is that remember that the inverse of a trig function just gives me an angle. So this is just an angle theta. So I'm just going to say this theta is equal to cosine inverse of x. So basically my new equation is y equals sine of the inside, which is just theta. Okay, so we got to figure out what exactly is this. So right now we know that theta is equal to cosine inverse of x. Move the cosine over, so you have cosine of theta equals x. So now what we're going to do, we're going to write a right triangle. Okay, so here's theta. The cosine is the opposite, the adjacent over the hypotenuse, which is going to be 1 in this case. So then using Pythagorean theorem, you can see that this is going to be the square root of 1 minus x squared. Okay, just using the Pythagorean. So then what we want to figure out, and remember that we want to figure out what exactly the sine of theta is. Well, the sine of theta will be the opposite over the hypotenuse, which in this case will be the square root of 1 minus x squared divided by 1, but that can go away. So now what we have is that y is equal to the square root of 1 minus x squared. So I'm going to square both sides. So you get y squared equals 1 minus x squared. And then notice that when I add the x squared over, I end up with x squared plus y squared equals 1. There you go. That's how you solve it algebraically. So the cosine and the sine, whenever you have them as parametric equations, you are going to get some sort of circle. Okay, in this case, you got this type of circle. Now, what I want you to do, and I won't do it here, but I just want to give you guys a little glimpse that sometimes, depending on what you have in front, so let's say I have the 2 cosine t, and you have y is equal to 4 sine t. These are still going to be circles, but because I'm extending the amplitudes, you're actually going to have something that's a little bit more lopsided. So the circle is now going to look something like this, which is what we call an ellipse, and it should be more centered. This is terrible. So it's going to look more like this. So why don't you try to graph this, and you will see that you have this type of elliptic thing that we constructed when we graphed this. So try it out on your own. You don't need to evaluate the parameter. You can, of course. And actually, when you do it, what I would suggest is do the same thing: cosine squared t plus sine squared t equals 1. And then in order to solve for it, why don't you solve for the sine and the cosine by moving that over, and then you'll be able to see that that's going to be the equation of the ellipse. So just try it out, and then but you can practice it, and you can see that you actually get this ellipse.